Let's solve Unit 5 System Software and Operating System questions. Match the list 1 with list 2. The RAID level details are given in list 2. RAID 0 is for non-redundant stripping. RAID 1 is for mirror disk. A will be mapping to 2, RAID level 1 for disk mirroring. RAID 2 will be memory style error correcting code. B will be mapping to 4, ECC organization. ECC will be error correcting code. RAID level 3 will be bit interleaved parity. C will be mapping to 1, bit interleaved parity organization. RAID level 4 is block interleaved parity. D will be mapping to 3, block interleaved parity organization. RAID level 5 will be block interleaved distributed parity, and RAID level 6 will be P plus Q redundancy. This has been a repeated question in few of the previous year question papers. We have A2 in 2 of the options, so we can remove 3 and 4. Then we have B4. A2, B4 is available only in option 2. We will even rule out option 1. Option number 2 will be the right answer. Then we have C1 and D3 also. Next question. Given the following processes with their times and priority, lower number indicates higher priority. Which of the following is a value of average waiting time using priority scheduling algorithm? In priority scheduling algorithm, the processes will be arranged as per priority. So out of 3, 1, 4, 5, 2 in the priority column, which is the lowest number here, it is 1. So definitely this particular process will have higher priority. So let's arrange the processes as per priority order. P2 will come first, then we have P5, then we have P1, then we have P3, and then we have P4. Now they are asking for the average waiting time. It means you have to calculate the waiting time of every process, sum them up and divide it by the number of processes. So we will start with P2 because it is going to get executed first. What is the waiting time of P2? When P2 enters, it automatically gets executed. So the waiting time will be 0. What about P5? P2 has a burst time of 1. After P2, P5 will start executing. So it has to wait for 1 unit of time. What about P1? P2 has a burst time of 1 and P5 has a burst time of 5. 1 plus 5 is equal to 6. So it has to wait for 6 units. What about P3? Along with 6, you have to add 10. 1 plus 5 plus 10. 10 plus 6 will give 16. So P3 has a waiting time of 16. What about P4? 16 plus 2. The waiting time will be 18. Now we have to sum the waiting time. 0 plus 1 plus 6 plus 16 plus 18, which is equal to 7, 23. 23 plus 18 will give 41. How many processes are there? Overall 5 processes are there. So 41 divided by 5. This will give you the average waiting time. 41 divided by 5 will give you 8 5s are 40.2. 8.2 will be the right answer. It is available in option number 4. Option number 4 will be the right answer. Next question. If the virtual memory size is 32 MB and a physical memory size is 4 MB with a page size of 2 KB, calculate the number of frames available in physical memory. Here the question is about physical memory. So we are not going to touch this virtual memory size data. This will not be needed for this particular question. Number of frames is given by the size of physical memory divided by page size. What is the size of physical memory? It is 4 MB divided by the page size is 2 KB. Numerator and denominator are in different units. We know 1 kilobyte is equal to 1024 bytes. 1 megabyte is equal to 1024 kilobytes. What we can do is we can convert the numerator to kilobyte and thereby cancel both the units in numerator and denominator. So let's have 4 as it is. Instead of megabyte, we will go with 1024 kilobyte divided by 2 kilobyte. Now kilobyte and kilobyte unit will get cancelled. 2 2s are 4. So you have 2 into 1024 in the numerator. There is nothing in the denominator. What is 1024 into 2? It is 2048. So what will be the number of frames? It will be option number 2, 2048. Option number 2 will be the right answer. Next question, which of the following does not interrupt a running process? Device, timer, scheduler, power failure. Now we'll look about all the options. Devices can interrupt a running process. For example, when an I/O device like a keyboard or mouse needs some kind of attention, it generates an interrupt to notify the processor, causing the running process to be temporarily halted. So whenever there is a device that is requesting for a service, it always generates an interrupt to the processor. So definitely device will be interrupting a running process. They are asking for does not interrupt. So we can rule out device from the answer list. Then we'll go for timer. A timer interrupt is used by the operating system to preempt the current running process. So this is also going to interrupt a running process, so this will also not be the answer. This timer interrupt allows the OS to enforce time sharing and ensure that all processes get a chance to execute, preventing any single process from taking control over the CPU. What about scheduler? The scheduler does not interrupt a running process. Instead, it decides which process will run next when the current process either completes or is preempted by an interrupt. Like a timer or a device, we can say. The scheduler's job is to manage the execution order of processes and they do not directly interrupt them. In that case, we can say it does not interrupt a running process. What about power failure? A power failure results in an immediate halt of all processes since the system loses power. This is an abrupt and involuntary interruption that affects all running processes. Whether it is voluntarily done or involuntarily done, here there is an interruption occurring. So definitely power failure will also interrupt a running process. So we can rule out even option 4. So what will be the right answer? Option number 3, scheduler will be the right answer. So when you are learning which does not do some task, always learn about the other options which are involved in doing that particular task, because it might be helpful for you in some other question paper. Next question. The entire set of parameters including return address that is stored for a procedure invocation is referred to what? Stack frame, stack base, stack limit, stack record. So we will learn about all the 4 options. A stack frame, also known as an activation record, is the entire set of parameters including the return address, local variables and other information that is stored when a procedure, that is when a function is called. The entire set of parameters including return address, that is what is given here. Entire set of parameters including the return address is stored when the procedure is called is equated to stored for a procedure invocation. Invocation means it's calling. Stack frame will be the right answer. Option number 1 will be the right answer. Each procedure call creates a new stack frame, or we can say a new activation record, which is pushed onto the stack and popped off when the procedure completes. So if you take a stack like this, say for example there are 2 procedures P1 and P2 getting executed. The first call is P1, so we will have P1 in the stack and P1 will call P2, then we will have P2 here. Once P2 gets completed, it is popped off and the control moves to P1. Once P1 is also done, it will be removed from the stack. So this is actually used to maintain the order of procedure calls also, we can say. What about stack base, stack limit and stack record? The stack base is a pointer that refers to the base or starting address of the stack. It is not the entire set of parameters for procedure invocation, but it's just an address indicating where the stack begins. So this is not the answer. The stack limit refers to the maximum allowable size of the stack or the boundary beyond which the stack cannot grow. This is a constraint to prevent stack overflow but does not represent the set of parameters for a procedure invocation. Actually, there is no term like stack record. Actually, we call it as activation record and not stack record. While stack record can sometimes be interchangeably used with stack frame, it is actually less commonly used in this context. So we cannot consider this particular term as an option at all. Next question. Consider the following graph of disk scheduling and identify the disk scheduling algorithm represented by this graph. They have given the queue as 84, 125, 11, 36, 170, 20, 172, 45. From the graph you can understand the head position is actually given in 28. We will see the graph as per every scheduling algorithm that is given in the 4 options. Whichever representation is matching with the question graph, that particular algorithm will be the answer. Let's start with shortest seek time first, SSTF. This selects the request with the minimum seek time from the current head position. Taking the first position as 28, we have two ways. We can either go to 36 or to 20. 28 plus 8 will give you 36 and 20 plus 8 will give you 28. So both are possible here. After 36, if you go, you will have 45 with 9. Then here we have again 9, 11. From 45 you have to move to 84. What is 84 minus 45? 14 minus 5 is 9. 7 minus 4 is 3. At a distance of 39 you have 84 here. What about 45 and 20? At a distance of 25 you will have 20. Then again with a distance of 9 you will have 11. After 11 you have to directly go to 84. What is 84 minus 11? It will be 73. So from 11 there is only one way to move forward, that is 36. So you have only 25 movements here. From 36 it is 45. From 45 it is 84. So we will take this particular order in SSTF. 28, 20, 11, 36, 45, 84, 125, 170, 172. This will give the shortest seek time compared to other ways. Is the graph moving towards 20? No. So option number 1 is wrong. What about the next algorithm? Scan. In the scan algorithm, the disk arm starts at one end of the disk and moves toward the other end, servicing request as it reaches each cylinder until it gets to the other end of the disk. At the other end, the direction of head movement is reversed and servicing continues. They are saying it will move till the other end of the disk. It means what is the end here? 199. So we will start with 28, then move towards 36, 45, 84, 125, 170, 172. From 172 we have to touch this 199. From 199 we have to reverse the direction of the head movement and then servicing continues means you have to start with 20 and then move to 11. Is this particular graph touching 199? No. Scan is also out of the race. What about C-scan? C-scan moves the head from one end of the disk to the other, servicing request along the way. When the head reaches the other end, however, it immediately returns to the beginning of the disk without servicing any request on the return trip. It means once it touches the other end, which is 199, it has to immediately return to the beginning of the disk without servicing any request. After 172 it is moving to 11, but it is not touching 199 or 0, which is in the path of C-scan movement. So C-scan is also not in the option. What about C-look? C-look is similar to C-scan but does not move to the end of the disk, but the arm goes only as far as the final request in each direction. It means 172 is the final request towards one end and 11 is the final request in the other end. So the travel will be till 172 in this end and 11 in this particular end. Then it reverses direction immediately without going all the way to the end of the disk. It means it will go only till 172 and not to 199. It will reverse direction immediately when it finds the first request. You have 11 in the first place. Without going all the way to the end of the discus, it will stop at 11 but it will not go to 0. Now you can have the order as 28, 36, 45, 84, 125, 170, 172. From 172 we are moving to 11. From 11 we are going for 20. This graph is also giving the same order. 28, 36, 45, 84, 125, 170, 172. Without touching the other end 0, it is stopping at 11. Then it is servicing the request at 20. So this graph representation is equated to C-look descheduling algorithm. Option number 4 will be the right answer. In order to answer this particular question, you should have understanding about all the descheduling algorithms. Next question. From here we are going to answer for a set of 5 questions. Consider the following set of processes with the arrival time and length of CPU burst time given in milliseconds. What is the average turnaround time for these processes with first come first serve scheduling algorithm? The first question is with respect to FCFS. So in whatever order it is arriving, it will be executed in the same order. This is the order of execution. What is turnaround time? It is completion time minus arrival time. We have to know the completion time in order to calculate the turnaround time. At time 0, P1 is entering. It is executing for 5 milliseconds. What is the completion time? It is 5. P2 actually arrived at 2, but till 5 it didn't get the CPU. So from 5 it has to run for a burst time of 3. This will run up to 8. The completion time of P2 will be 8. From 8, P3 will be running for 2 burst time. This will be 10. From 10, P4 will run for 3 milliseconds. This will be 13. From 13, P5 will run for 1 millisecond. So this will be 14. So this is running for 5 burst time. This is for 3 burst time. This is for 2. This is for 3. And this is for 1. Since the process is served in first come first serve scheduling algorithm, we are going with the same order as per the arrival time. Now we have the completion time. So what we should do for turnaround time? It is completion time minus arrival time. 5 minus 0 will give you 5. 8 minus 2 will give you 6. 10 minus 2 will give you 8. 13 minus 5 will give you 8. 14 minus 6 will give you 8. They are asking for average turnaround time. This will be 5 plus 6 plus 8 plus 8 plus 8 divided by how many processes are there? 5 processes are there. 8 plus 8 plus 8 is 24. 24 plus 6 is 30. 30 plus 5 is 35. 35 divided by 5 will give 7, which is equated to 7.0 milliseconds. Option number 3 will be the right answer. Next question. What is the average waiting time for these processes with non-preemptive shortest job first SJF scheduling algorithm? What is actually non-preemptive? When P4 is executing, P5 is entering with 1 burst time. If they say it's a preemptive SJF, immediately the control moves to P5. But they have told it is non-preemptive. It means once a particular process gets the CPU, until it completes, it will not allow any other process inside. Once a process starts executing, it runs to completion before another process is selected. It doesn't get interrupted or swapped out is what we mean by non-preemptive. Let's take the tabular column here. The arrival time and the burst time is given as it is. We are going by shortest job first. Just don't go with the burst time. We cannot go and select P5 initially because P5 is only arriving at 6 millisecond. Which process is actually arriving at 0th millisecond? P1. So P1 will get the first execution slot. What is the burst time of P1? It is 5. So P1 will be completing at 5. We will have 5 here in completion time. P2 has arrived at 2. P3 has arrived at 2. Since the time is actually 5 millisecond, P4 has also arrived at 5 millisecond. So we will have P4 is equal to 5. Now just consider the burst time alone. P2 is 3, P3 is 2 and P4 is 3. Which is having the shortest job here? P3 is having shortest job. So P3 will be selected next. For how much burst time it should execute? For 2 burst time. So 5 plus 2 will give you 7. The completion time of P3 will be 7. Now at 7 milliseconds, we already have P2 that has been arrived at 2 millisecond, P4 that has arrived at 5 millisecond, and we have P5 also at 6 millisecond. So now this is the arrival time. What about the burst time here? P2 has 3 burst time, P4 has 3 burst time and P5 has 1 burst time. Which is having the shortest job? P5. So we are going with P5 now. P5 will execute for 1 burst time and the completion time will be 7 plus 1 which is equal to 8. After P5 we have only 2 options. P2 with 3 burst time, P4 with 3 burst time. So based on the arrival criteria we will first execute P2 itself. P2 will run for 3 burst time 11 and P4 will be alone remaining here. So P4 will run last for 3 milliseconds and thereby complete at 14. So P2 will complete by 11 and P4 will complete by 14. Now what is turnaround time? It is completion time minus arrival time. These two columns have to be taken now. 5 minus 0 is 5, 11 minus 2 is 9, 7 minus 2 is 5, 14 minus 5 is 9, 8 minus 6 is 2. What about the question? They have asked about the average waiting time. So here we can use this particular formula, turnaround time minus burst time. These two columns can be considered here. What is 5 minus 5? It is 0. So P1 has 0 waiting time. It is done. What about P2? 9 minus 3 is 6. Why P2 is having 6 waiting time? It's because P2 is getting the slot only at 8. But when did it come? It came at 2. So 8 minus 2 will give you 6. You can even compute in that way if your mind works better during examination. But if you know this formula, it will be easy for you to compute. Next, what about P3? It is 5 minus 2 which is 3. So P3 is actually arriving at 2nd millisecond and it gets the CPU at 5th millisecond. So 5 minus 2 will give you 3 only. What about P4? 9 minus 3 is 6. P4 arrives at 5 but it gets the CPU only at 11. 11 minus 5 will give you 6. What about 5? 2 minus 1 is 1. P5 is arriving at 6 but it gets the CPU at 7th millisecond. So it is waiting only for 1 millisecond. If you are able to get it in that way, you can go by that. If you are not able to process it, then you can go by this formula. There is no compulsion that you have to do only in this way. But ultimately, you should get the right waiting time. That alone you have to keep it in the mind. What about the average waiting time now? Sum them up. 0 plus 6 plus 3 plus 6 plus 1 divided by the number of processes which is equal to 5. 6 plus 3 is 9, 9 plus 6 is 15, 15 plus 1 is 16. 16 divided by 5. 5 3s are 15, then we have 0.2 for 10. 3.2 millisecond is the average waiting time here. Option number 4 will be the right answer. Next question. Find the average weighted turnaround time for this process using highest response ratio next algorithm. HRN algorithm they have given. Actually it is HRRN algorithm. HRRN is a non-preemptive scheduling algorithm where the process with the highest response ratio is selected next. What is this response ratio? Waiting time plus burst time divided by burst time. Why is this particular response ratio useful? Because sometimes a process may come earlier, but due to its long burst time, it has to wait for a very long time. In order to not allow process suffer more of starvation, this response ratio will be useful. What is the question about average weighted turnaround time? So for weighted turnaround time, we need turnaround time divided by burst time. What is turnaround time? It is completion time minus arrival time. We have to find the completion time, turnaround time, and from there we have to get weighted turnaround time. Let's take 0 millisecond first. At 0 we don't have any process, so P1 will be getting the CPU. What is the burst time of P1? It is 5. So till 5 milliseconds it is getting executed. Now which process has to be selected next? At 5 milliseconds, what are the processes available? P2, P3 and P4. The arrival time for P2 and P3 will be 2 and the arrival time for P4 will be 5. So at 5 milliseconds these three processes are ready. We have to find the response ratio of these three processes. So what is the arrival time here? Let me write it here. It is actually 2, 2 and 5. Let's take the time here as at 5. Just to find out this particular slot, we are going with this particular calculation. What is the waiting time of process 2? It arrived at 2 and now the time is 5. So 3 milliseconds. P3 is also waiting for 3 milliseconds. P4 arrived at 5 only and now the time is 5 only. So 0 milliseconds of waiting time. What is the burst time of these processes? P2's burst time is 3, P3's burst time is 2, P4's burst time is 3. Now we have to find the response ratio. Waiting time plus burst time divided by burst time. 3 plus 3 divided by 3. It is 6 by 3 which is equal to 2. Then we have 3 plus 2 divided by 2. It is 5 divided by 2 which is equal to 2.5. What about P4? 0 plus 3 divided by 3. 3 divided by 3 will give you 1. We have to select the process with the highest response ratio. Which is having the highest value here? 2, 2.5, 1. P3 has the highest value. So we have to go with P3 based on this particular value. So P3 will get the CPU next. What is the burst time of P3? It is 2. 5 plus 2 will give you 7. At time 7, what are the processes available? P2 is there, P4 is there and P5 is also there. What is the arrival time? P2 is 2, P4 is 5, P5 is 6. What about waiting time? Now the time is 7 milliseconds. 7 minus 2, it has waited for 5 milliseconds. 7 minus 5, it has waited for 2 milliseconds. Then 7 minus 6, it has waited for 1 millisecond. What about the burst time? P2 is 3, P4 is 3, P5 is 1. Now we have to calculate the response ratio. 5 plus 3 divided by 3. 8 by 3, this will give a value of 2.666. It goes on. So we can round off to 2 decimal places, 2.67. What about 2 plus 3 divided by 3? It is 5 divided by 3. Here we have 1.66. So we can round off to 1.67 here. What about P5? 1 plus 1 divided by 1 will give a value of 2. Now 2, 1.67, 2.67. Which is having highest response ratio? This process. We are selecting P2 here. P2 will get the next slot. What is the burst time of P2? It is 3. 7 plus 3 will give 10. So P1 is completing at 5. P3 is completing at 7 and P2 is completing at 10. At 10 milliseconds. What processes are there? P4 and P5 are there. P4 arrived at 5 and P5 arrived at 6. What about waiting time? The current time is 10. 10 minus 5 is 5. 10 minus 6 is 4. What about burst time? It is 3 for P4 and 1 for P5. What is the response ratio? 5 plus 3 divided by 3. 8 divided by 3 will give 2.67 and 4 plus 1 divided by 1 will give 5. Which process is having highest response ratio now? 5. So P5 will be selected now. We'll go with P5. What is the burst time? 1. 10 plus 1 is 11. P5 is getting completed by 11 milliseconds. What is the remaining process? It is P4. So let's have P4 here in the final slot. What is the burst time? It is 3. So 11 plus 3 will give you 14. The completion time is 14 here. What about turnaround time? It is completion minus arrival time. 5 minus 0 is 5. 10 minus 2 is 8. 7 minus 2 is 5. 14 minus 5 is 9. 11 minus 6 is 5. Now we have to find the weighted turnaround time. It is these two columns. Turnaround time divided by burst time will give you weighted turnaround time. 5 divided by 5 will give you 1. 8 divided by 3 will give you 2.67. We have already calculated here. Just go with 8 divided by 3. 3 2s are 6. You have 20 here. You have 0.6. Again you keep having 20 again and again. So instead of going as 2.666, we are just rounding off to 2 decimal places. That's why we have 2.67. Then we have 5 divided by 2, which will give 2.5 exactly. Then we have 9 divided by 3. This will give you 3. 5 divided by 1 will give you 5. So what is the average weighted turnaround time? 1 plus 2.67 plus 2.5 plus 3 plus 5 divided by 5. 3 plus 5 is 8. 8 plus 1 is 9. 9 plus 2.5 is 11.5. 11.5 plus 2.67 will be 7. 5 plus 6 is 11. 1 plus 1 is 2. 2 plus 2 is 4. 14.17 in the numerator. 14.17 divided by 5. 5 2s are 10. We have 4. Then we'll have a point. It's 41. 5 8s are 40. 41 minus 40 is 1. Then we have this 7. 5 3s are 15. And 7 minus 5 is 2. Then we have 5 4s are 20. So the value is 2.834 milliseconds. This will be the average weighted turnaround time. 2.834 milliseconds is available in option 2. Option number 2 will be the right answer. Next question. Calculate the average response time for these processes with non-preemptive priority scheduling algorithm. Priority of the process are as follows, and consider that all the processes came at 0 time. Note, low numbers represent high priority. What does this mean? All processes came at 0 time. We are not going with this arrival time. They are saying the arrival time of all the processes will be 0 only. So at a stretch you have to consider all the 5 processes. But the execution will go with priority scheduling algorithm. So you have to choose the process with the highest priority. So P2 is having the highest priority here. In non-preemptive scheduling algorithms, the response time is typically the same as the waiting time, because the process starts executing as soon as it is scheduled. So the order will be P2 first, then the second one will be P5, then we have P1, then we have P4, and finally we have P3. Now based on this, we have to find the average response time. In non-preemptive scheduling, the response time is equal to the waiting time, because once the process gets the CPU, until it completes, it will not get out of it. In preemptive scheduling, what happens is, let's take an example. P6 is coming in, and because of some priority, P7 is getting the CPU, and then P6 is again getting the CPU. This waiting time is what we can call as response time. We are not worried about when it is going to complete. So there are possibilities of splitting up of the execution of the same process in preemptive scheduling. In non-preemptive scheduling, such a scenario will not happen. So the response time is typically the same as the waiting time. So if they have asked you average response time, it means you have to calculate the average waiting time. So let's start from 0. So every process is going to have 0 arrival time. So the first process here will be P2. P2 will run for 3 milliseconds. So the completion time of P2 will be 3. After P2 we have P5 for 1 millisecond of burst time. So this will be 4. P5 will complete at 4. After P5 it is P1. It will run for 5. 4 plus 5 will give you 9. So it will complete at 9. After P1 it is P4. So 9 plus 3 will give you 12. So this will be 12. After P4 it will be P3 finally. P3's burst time is 2. So it will complete at 14. Now we have to just compute the waiting time. P2 does not wait for any time. So the waiting time here it is 0. P5 is waiting for 3 milliseconds and starting. So it is 3. So this is P5's wait time. So here at 0, P1, P2, P3, P4, P5 all are ready. Now P5 is starting at 3 means what is the wait time? It is 3. P1 is starting at 4 means what is the wait time for P1? It is 4. P4 is starting at 9 means what is the wait time? It is 9. P3 is starting at 12 means the wait time is 12. Turnaround time will be equivalent to completion time because turnaround time will be completion time minus arrival time, which is 0 in all the cases. So this will be automatically the turnaround time. Now what is wait time? It is TAT minus BT, that is turnaround time minus burst time. Just compute these two columns. 9 minus 5 is 4, 3 minus 3 is 0, 14 minus 2 is 12, 12 minus 3 is 9, 4 minus 1 is 3. So let's take average response time is equal to, we have to consider 4 plus 0 plus 12 plus 9 plus 3 divided by 5. 4 plus 12 is 16, 16 plus 9 is 25, 25 plus 3 is 28 divided by 5. 5 5s are 25. We have 3. It is 0.6 for 30. 5.6 milliseconds will be the average response time. Option number 1 will be the right answer. Next question, in fact the final question of the set of 5 questions. When we apply shortest job first scheduling policy algorithm, process P2 faces partial starvation and waits for the longer time to execute. Which one of the following algorithms addresses this problem? So let's actually take every algorithm now. In round robin scheduling, each process gets an equal time slice or a quantum in a cyclic order. While this algorithm prevents starvation and is fair in terms of time allocation, it may not be the most efficient for minimizing response time or turnaround time for processes with shorter burst times. So this is not going to do much change, but it will not allow any process to starve. That is also true. What about priority scheduling? In priority scheduling, the process with the highest priority is selected for execution. While this can be effective, this can also lead to starvation if lower priority processes are constantly preempted by higher priority ones. Take for example, if a process keeps coming with highest priority, when you have something in low priority, it will never get a chance to get executed. That is what they say here. What about least completed next scheduling algorithm? So this is for option 1, this is for option 2 and this is for option 4. This algorithm is not commonly defined in classic scheduling. It might imply choosing the process with the least progress or shortest remaining time, similar to SRTF algorithm, shortest remaining time first. Like shortest job first, it can lead to starvation for longer processes if shorter processes keep arriving. Definitely starvation for longer processes will occur if upcoming processes are completely having shorter burst times. So let's see the P2 process in SJF and the P2 process in highest response ratio next algorithm. This is the order of arrival. As they say, it faces partial starvation. Actually, it should have started second, but it is starting fourth is what they say in SJF. This is the situation explained in the question. This algorithm is actually moving the P2 process from the fourth slot to the third slot. So HRRN algorithm will address this problem. HRRN considers both the waiting time and burst time when selecting the next process to execute. What is response ratio formula? Waiting time plus burst time divided by burst time. So it is considering both waiting time and burst time when selecting the next process. By selecting the process with the highest response ratio, HRRN balances between short and long burst time processes, ensuring fairness. So they are saying how it is addressing this particular problem. This ensures that processes that have been waiting for a long time get a higher priority, thus preventing starvation. At one point of time, this particular ratio value will be higher due to higher waiting time. At that time, it will get some kind of higher priority in response ratio calculation, and thereby it will be given the CPU. So which algorithm actually addresses this problem is highest response ratio next algorithm, which is available in option 3. Option 3 will be the right answer. I have given you the explanation of round robin priority with respect to starvation of processes. And least completed next is actually not a part of CPU scheduling, but just based on the term least completed, we can compare it to shortest remaining time first or shortest job first. So considering this case, definitely it will lead to starvation is what they say. But when you don't have an algorithm with this term, you need not consider them at all. Compared to HRRN, round robin and priority scheduling will not address this problem. So we can even rule out option 1 and 2. With this, we are completing Unit 5 solutions.